Hello. Here we're starting chapter 8, which is about power series and finding power series solutions to differential equations. And we've seen some power series in the past. We've used Taylor series in particular to approximate solutions to differential equations. And in this chapter, we're really going to focus on actually finding the true solution that takes the form of a power series. And so to motivate this a little bit more, we're going to just start off with an example. So let's consider our differential equation, y prime equals 1 over x plus y plus 1, and an initial condition, y of 0 equals 0. So now we know from calculus that we can approximate functions. Say we have some f of x. We can approximate it with a Taylor series that looks like some value, the f at some particular x naught value, plus f prime at x naught times x minus x naught, and then a double derivative over 2 factorial. Always forget that part. And then we can take this up to, say, n derivatives. Let's make ourselves a little bit more space. Times x minus x naught to the n over n factorial. So this is an approximation of f of x for x near our sort of center point, x naught. And we can say it's usually gets better for larger n. Oops. Larger n. So that means that the more terms you add to this Taylor series, the better of an approximation you're going to get to your original f. So we're going to look at our differential equation now. We know something about y at one point, and then we know something about the derivative. And so we can use that derivative, this sort of prescription about what the derivative of y does, to figure out what the coefficients for our Taylor series is going to be. And maybe we can do that for a couple points and get a reasonable approximation to our solution. So we will compute a Taylor series approximation for y of x near x equals 0. Okay, so we already know that, let's say, y of 0 equals 0. And then y prime of 0, well, we can just plug in. So that's going to be 1 over 0 plus y of 0 plus 1. Y of 0 equals 0, so this equals 1. Now, if we want the second derivative, then we can take the second derivative by just taking the derivative of our differential equation. So y double prime is going to equal negative times the denominator, it's 1 to the negative 2, oops, the negative 2, times the derivative of the inside, or which is going to be 1 plus y prime. And then we can plug in 0 and everything. So y double prime at 0 is going to be equal to 1 plus y prime at 0, quantity negative, over 0 plus y of 0 plus 1 squared, which equals negative 2 over 1 was negative 2. Now let's just do this one more time because it's fun, I guess. And so we can compute y triple prime, which is going to be equal to, let's rewrite this as negative 1 plus y prime over x plus y plus 1 squared, and then we can do quotient rule for y triple prime. So let's see, low d high x plus y plus 1 squared times negative y double prime minus plus high 1 plus y prime d low. So we've got 2x plus y plus 1 times 1 plus y prime. This is long. Over low squared, so we've got x plus y plus 1 to the 4th. And now we can plug in y triple prime of 0 is going to be negative 0 plus 0, because x is 0, y of 0 is 0, plus 1 squared. Y double prime was negative 2 at 0, plus 1 plus y prime at 0 is 1 times 2 times that whole quantity x plus y plus 1 is 1, and then 1 plus y prime at 0 is 1, and this whole thing over 1 to the 4th, which is going to equal, let's see, we've got a 2 plus 2 times 2 times 2 is 8 over 1, which equals 10. And amazing, that's the same thing that's in the book. Okay, so that's probably enough. Now we can get our estimate for our solution to our differential equation. Y of x is roughly equal to y naught plus y prime at 0 over, there we go, times x plus y double prime over 2 factorial times x squared plus y triple prime, that's at 0 over 3 factorial x cubed. And now I have my x and x squared and x cubed because my x naught equals 0. And so that's what I'm plugging in for these sort of factorial, or those polynomial terms up there. So let me point that out. X naught equals 0. And now I can just plug in the values that I computed. And I've got 0 for this one. Y prime at 0 is 1, so x minus 2 over 2 factorial is 1 times x squared. And then y triple prime at 0 is 10, so 10 over 3 factorial is 5 over 3 x cubed. So now this is an approximation, and we could say things about sort of how good of an approximation it is. We talked about that back when we were doing the Euler approximations. But this chapter is not really about doing approximations. It's more about using power series to compute the actual solution. And so if what I said about the approximation error or the goodness of the approximation getting better the more terms you add. So we want to ask the question, when can you use infinitely many terms? And another way to think about that would be when does let's see, maybe I should have written y. When does our function actually equal exactly the infinite power series or Taylor series, k equals 0 to infinity? So now I'm going to start using my summation notation, which looks like y at x0 to k over k factorial times x minus x naught the k. Okay. And that question is, when can you represent a function by its power series, is going to be answered in this section. So instead of talking just about specific Taylor series, I'm going to talk about power series in general. So hopefully you've seen a lot of this in your calculus classes before, but it's a reasonable thing to review because it's not an easy subject, especially the first time you see it. So let's do a definition. A power series about a point x naught is an expression sum from n equals 0 to infinity, some an, a coefficient, times x minus x naught to the n, okay? And so if we sort of wrote this out, this would look like a naught plus a1 x minus x naught plus a2 x minus x naught squared, yada, yada, yada. So it's an infinite polynomial, and instead of having x's and x squares and x cubes, you've got x minus x naught because we want to be sort of centered around a point. And then we have our coefficients, these an or a naught, a1, a2, etc. These are called the coefficients. And so if you look at the Taylor series that we have drawn up here, this would be like the an, or ak in this case. So just, I guess, to throw you off, I used a k up here and I used an n here, and that letter is just kind of a dummy variable, the way that you have a dummy variable in an integral, and you can sort of swap it out and change it depending on what you want to do. And so this is an infinite series, which means that you're adding up an infinite number of things. And if those things are too big, then you're just going to add up an infinite bunch of numbers and not converge to anything. And so it's worth noting whether a power series converges or doesn't. So we say the power series converges at a particular point So now if you plug in a value for x, then you get just an infinite series. It's not a power series anymore, it's just a series of numbers. It's just a bunch of numbers getting added together. So if the infinite series n equals 0 to infinity a n c minus x naught to the n converges. And another way to say that is if the limit as n goes to infinity, big N goes to infinity of the partial sum n equals 0 up to big N. So if you add up the first n numbers and then add up the first n plus 1 numbers and then n plus 2 and do that and so forth, then you get a sequence of numbers which are separated by commas instead of plus signs. And so if that sequence of numbers, a n c minus x naught to the n, is finite. There you go. Otherwise, if that limit is infinite, the power series diverges at x equals c. So if we have a function y of x and we want to be able to represent it as a power series, then we need that power series to converge, because if that power series sort of equals infinity, then it's not going to be the same as y, which is a finite valued function. So the answer for which x values a power series converges is basically the values close to x naught. And that is sort of solidified in this theorem, which again you've probably seen before. So for each power series of the form just what I wrote before, sum from n equals to infinity, a n x minus x naught to the n. There is a number, rho, looks like a p, and rho could be 0, and it could be infinity, or it could be anything in between. And this is the radius of convergence. Of the power series. Okay. And what's relevant about that, such that I'm going to call this up here, this power series PS. So our power series will converge, absolutely. We didn't define that, but that's okay. For x minus x naught less than rho. And diverges for x minus x naught greater than rho. So if the power series converges for all values of x, then we say rho equals infinity. And if the power series PS converges only at x naught, then we say rho equals 0. So of course it's going to converge for x equals x naught, because if x equals x naught, then all of these terms are going to be 0. And so the only term from this power series you'll get is the first n equals 0 term. So just the first coefficient. And that'll be a number, and of course it converges. And so we can sort of visualize what we just said on a number line. So we're sort of centered at an x naught. So this is our interval of convergence. And we get some rho. And so if you go x plus rho, and then sort of the same distance over to the other side, x naught minus rho, then in here, we get absolute convergence. And what absolute convergence means is that you can, if you put absolute values around the x minus x naught, then it converges. And usually that ends up making not a big difference, but sometimes it does. But that's getting into a bunch of series stuff that we're not really going to talk about. And then outside of here, we're going to diverge. Divergence. And then right at these values, sort of unknown. You've got to check those things individually. So now I'm really relying on you having seen this stuff in calculus, because I kind of don't want to go over it all. But we have the ratio test, which will help us find rho. So this theorem says if for n large, the coefficients an are non-zero and satisfy this, so you take the ratio of adjacent coefficients and see where that goes as n goes to infinity. And if it's fine, or if it's some number, could even be infinity, then the radius of convergence of our power series PS is rho equals L. So there are some examples of this in the book and in the homework, and I hope you've done it in calculus. If the limit doesn't exist, it might not even be infinity. Like if it's infinity, that's good, but it might just sort of oscillate around and then it doesn't tell you anything. There are some other methods that you can use, like the root test and blah-de-blah. So, but this is sort of the easiest way to find rho if it works. And then you can check the values at the endpoints of your radius. And so I'm gonna not do an example here, but you can see example 1 on page 427, if you want a refresher on that. There's also Khan Academy videos that I'll link to. Okay, this video is getting long, and I've got another one to do the other half of this video, or this section, but I'm gonna do one more result before I finish. So we've got this theorem that we've used similar things before, and we're gonna use them a lot. So if the sum from n equals 0 to infinity, this power series, x, same thing. If this equals 0 for all x in an open interval, so that means not just at a single point, it means like from some a to b and all the points in between there. Then each coefficient an equals 0. And I'm not going to prove this, but the idea is similar to how when we would say if ax squared plus bx plus c equals 0 for all x, if that polynomial is identically 0, then that tells us that our coefficients a, b, and c are equal to 0. So we've used results like that a lot in the past, and then we'll continue to use that in the rest of this chapter. So that's sort of the first half of the chapter, and I'm going to talk about some of the results in our next video.